I'm Michael Wolf from NVIDIA. I've been working in the PGI compiler team for 20-some years, been working on compilers for more than 4 decades. How many of you are not 4 decades old? A few, yeah, there you go. So I have a couple of highlights today. I'll be talking about ARM and ROM and mostly about GPUs. PGI has been coming to this show for 30 years. Now as part of NVIDIA, we're continuing that tradition. So PGI has been in business for a long time, since, in fact, 30 years. We've been developing the PGI compilers for over 30 years. These are optimizing real compilers for real languages. Real programmers doing real applications use our compilers on real supercomputers. We'll talk a little bit about that later. It has all the standard features and optimizations. We have a lot of accelerated computing features. I'll go into very briefly some of these. CUDA Fortran, if you're a CUDA programmer and you're a Fortran programmer, this is your solution. It's CUDA in Fortran. If you're not a CUDA programmer and you're not a Fortran programmer, you can ignore it. OpenACC Directives is another model for programming GPUs, works in Fortran, C++, and C. And we've been supporting x86 64-bit for a long time, and more recently Power, and now we've added support for ARM CPUs as well. So we'll be a full member of our platform. We'll have all the features of all the other compilers that we deliver. This is not available yet. It will be available for beta testing early next year and for final product delivery by the middle of next year. We're hoping to have it out for the next Community Edition release, if you know what that means. We support all the various important OSs. I do hear there's a Windows for ARM. We're not supporting Windows for ARM at this time. And we also have a new support optimizing for the really great AMD ROM CPUs. These are really hot CPUs. They've really done a nice job on their design. And here is our goal, is you have an application, all the source code up here. You want to deliver it on Skylake and make it run fast or whatever the next version of the Intel processor is. But you also have customers or users that want to build it for the ROM or whatever the next AMD CPU is. And some of them use Power, and in the future some of these will be using ARM. You don't want to have to change your source code. You don't even want to have to change your makefile. You really want to type make on the appropriate systems, and the application should run. And we really can make that happen. Not everywhere, not all the time. There are some interesting platform differences between x86 and, say, Power and ARM. One of the more interesting and irritating one is the difference between char for C. On x86, it's signed. On Power, it's unsigned. That's a real big difference, actually, but that wasn't our choice. That's the way it is for their platform. But we can parallelize for multi-core CPUs. We can parallelize for the GPU as well, equally well on each of these platforms. And I'm going to show you an example, quite briefly, Quantum Espresso. If you come by the NVIDIA booth, you can get more details about this particular example. So Quantum Espresso is an app that does, I have no idea what it does. But this one happens to be written in CUDA. It was ported to a GPU using CUDA Fortran. It's a big Fortran app. For the CPU, it's all written and optimized in Fortran. For the GPU, they added some CUDA Fortran kernels. And we compiled it and ran it with no changes to the source code, no changes to the makefile for all 4 platforms. We ran the CPU code on Skylake. We ran the optimized GPU code on each of the 4 platforms, compared that performance to the Skylake, and you can see it's 3 times faster or more on the GPU than it was on all the cores of a dual-socket Skylake. You notice the ARM is a little bit slower. I believe this is because the ARM CPU we were using was not the fastest ARM you can get today. We got what we got, and that's what we had to run it on. I think that number can be improved, but nevertheless, it's within 10% of all the others, and so that's really quite good. And there's a nice demo in the developer zone at the NVIDIA booth there. And so a little bit about CUDA Fortran, very little bit, I'll go over this very quickly. If you're familiar with Fortran, you recognize the syntax. If you're familiar with CUDA, you recognize kernels and the launch of the kernels. One of the advantages of CUDA Fortran is we can add attributes to things like the variables, so you don't need to do API calls to allocate data or even to copy data between host and CPU. You do need to launch the kernels. You need to write the kernels with all the syntax that goes there. Or if your application is simple, you can use this simple directive and then the compiler will write those kernels for you. Now, this won't work all the time, but it worked in Quantum Espresso. Most of their GPU code is written using this directive, so it works in a lot of cases, works really quite well. But that's not what I'm here to talk about. Partly what I'm here to talk about is OpenACC. And so OpenACC is a set of directives to allow a programmer to offload code for GPU acceleration, or in fact, to write parallel code for CPUs as well. Now, I will never say parallel programming is easy, but you can make writing the program easy. Parallel programming, there's a lot of things. We're doing this for performance. You got to be thinking about things like data layout, like data structures, like data access patterns, like where is the parallelism in my algorithm, how to expose that parallelism. Then you have to write the program. The hard part is that first part. Writing the program should not be as hard. So with OpenACC directives, if you've not seen this before, they look similar in many respects to OpenMP directives. They have a little bit of as we'll get into, a little bit more portability between CPU and GPU. Here I'm saying this is loop is a parallel construct, and I'm marking the parallel loops. The compiler will define a schedule for whether, depending on what target, if you're doing a CPU target, it'll run the outer loop in parallel across the cores and try to vectorize the innermost loop. For a GPU, it'll create a GPU kernel out of the whole loop and spread some of the iterations across the block indices and some of them across the thread indices, if you understand what that means. You can add clauses and directives to control the data that gets moved back and forth. The PGI compilers will try to implicitly determine how much data needs to be moved back and forth. For a case like this, because this is a linearized 2D array, it probably would fail, so you would probably need to put in those data directives. This particular program will run like a dog. It'll be dog slow if you run this on a GPU, because I've got this outer convergence loop and I'm doing data movement every time. And data movement is slow relative to compute. The computes can be blindingly fast, but the program will be quite slow. So now, in order to make it fast, you move the data movement outside that loop. There's no more data movement inside the loop. Now this program will run really fast, and you can go one more step and make it faster and say, I want to do asynchronous operations, and I'll put in a synchronization clause down here. So now I'm overlapping the CPU part of launching the kernel with the GPU of executing the kernel, and I'm getting really good performance now, and this thing is going to scream. Okay, that's great. I can recompile this with no changes to run in parallel on the CPU. Everything, all the directives work the same. And if I use this interesting option that we have Tesla :manage, the PGI compiler option, the managed option says, for all dynamic allocation, put the memory in the CUDA unified memory, or CUDA managed memory. We call CUDA managed memory. Then you still have physically separate memories, but the memory is allocated in such a way that the GPU driver will page the data from the system memory to the GPU device memory and back on demand. So now these data directives become optional. And in fact, you can leave them out. And in many cases, I won't say all cases, in many cases, locality works, right? Virtual memory works. Caches work. They work because of locality. Locality works. Once the data gets paged on the GPU, if that's where you're doing all that computation, the data will just stay there. So in many cases, using the managed memory and using this option is sufficient that people stop. They don't bother to try to optimize the memory movement. And I won't say in all cases, because in a lot of cases you do need to manage the memory, but that's an option. And I was saying before, you can compile it for this GPU, you can recompile it for the CPU, and we have this nice compiler feedback. The compiler's telling you what it's doing. How many other compilers tell you what they're doing? And why do we tell you what the compiler is doing? Well, why are you doing this? You're doing it for performance. If you want performance, you need to pay attention to performance. If you're not going to pay attention, then you're not really that interested in performance. So we're giving you some feedback so you can look at it and say, yeah, that was a good idea. And in particular, in those critical cases, you can look and say, I can do a better job. The compiler's not as smart as it thinks it is, or Michael Wolf is not as smart as he thinks he is. I can adjust the clauses on those loops and get a better performance, and that happens a lot as well. All right, and I've been saying, I said, and I still claim, we designed OpenACC to support performance portability across multi-core CPUs and GPUs. It's actually designed to support other devices as well, but part of NVIDIA, we're going to support CPUs and GPUs. It's someone else's job to support other devices. I will not say it will ever support FPGAs, FPGAs are a different beast entirely. Right? We can have that debate afterwards. But nevertheless, so we took, there's these Spec Excel benchmarks. This is from Spec. This is a real benchmark suite. We took the Spec Excel 1.2. There's an OpenMP version. There's an OpenACC version. They're the exact same programs, doing the exact same algorithm, the exact same data set, so the computation times are comparable. And here we compile the OpenMP versions for Skylake, for Rome, for Power9. I don't have any ARM numbers to show here. We compiled them using the Intel compilers, and you won't see a IBM compiler number here because IBM did not submit a score. They did not submit a number here. So you can see the PGI compiler is a little slower than Intel here, a little faster than the Intel compiler there. You can see the power is not as fast as Skylake. And then we took the OpenACC version, and now we compiled it with, obviously, PGI, because the other compilers don't have OpenACC, and compiled it for Skylake and Rome. I don't know why we don't have a Power9 number there. I honestly don't know why not. It's a kind of embarrassing. You see these numbers are comparable with these numbers, and I get a nice speed up on the Volta over here. This is great. So I get portability across different systems. I get portability to a GPU, and I get a nice CPU. A nice speed up when I go to the GPU because these algorithms are amenable to GPU acceleration. And who's using OpenACC? Everybody. So one of the announcements that was made within the last week, and there was a nice presentation today at the NVIDIA Theater, which you can see the video of if you go look at find out where NVIDIA's putting those videos. It takes 2 days to get there, so don't look until Friday. But IBM Graph, this is, IBM owns the weather company. The weather company has a new weather model based on MPAS. MPAS was developed by a collaboration including NCAR, and they parallelized, it wasn't IBM or the weather company, MPAS was parallelized to run on GPUs by this collaboration using OpenACC. And the weather company took this, and now this is live. You have your iPhone, you have your other app, this is what it's using. This is live today. Then the big story about this is not just that it's OpenACC parallelized, they're running this on a cluster of less than 80 nodes. So it's not a supercomputer, it's a cluster. It would fit in the range of this carpet here. And they're using a 3-kilometer grid globally. No one else does 3-kilometer grid globally. They might do 3-kilometer grid over land surfaces, but not over the ocean, not over the poles. They're doing a 3-kilometer grid globally. And they're computing a new forecast every hour. No one else does a new forecast every hour. It's every 6 or 12 hours. And they can do this because it's been accelerated so effectively for in this case, using OpenACC. So I'm afraid you missed the theater talk, but you get to see the video. And here's more success cases. There was another presentation at the NVIDIA Theater yesterday about VAST. VAST is one of the top 3 applications in supercomputers worldwide. In many sites, it's the #1 application. It's ab initio solver for biochemistry. And it's a big deal. And they needed to port their code. They wanted to use GPU acceleration. They thought the algorithms were amenable for GPU acceleration. They started on a CUDA port, and they said, this means we have to support 2 versions because not all of our customers are going to have GPUs. So that was a non-starter for them. They have a lot of people. This is a live code. It's being changed continuously. So to maintain it and allow for continuous modification, they need a single source solution. So they started with OpenACC, and they found a great deal of success. What they found was the OpenACC port for this small portion was faster than their CUDA port. Now, it's not because OpenACC was better than their CUDA programmers. It's because with OpenACC, I could port a larger part of the code very easily in a very short period of time, and now the whole thing was better. So they said, this is the direction we're going to go. And that's what they've been able to do. And many of these others are doing the same thing. Gaussian and ANSYS Fluent, these are 2 more of the top 5 applications on supercomputers worldwide. Everybody. There was a nice presentation on Monday at the WACPAD conference about these guys at the consortium, the organization that does the Comprehensive Nuclear Test Ban Treaty testing for finding when there are nuclear weapons. And this is a very underfunded organization. They don't have money, they don't have many people. They wanted to speed up their program to get better testing. And they had one guy, and he learned how to use OpenACC by himself. They bought a DGX system, and he got it running. It showed some really impressive speedups. So this stuff really works. Yes, there we go. And this is a quote from one of the key developers of VAST, showing this was key to their development process and maintenance effort. And you can come and see a demo. We're demonstrating this today. Martine, who's the lead developer, leading the development of VASP, is actually in the booth, has been in the booth almost continuously for the past couple of days. And I'm going to jump in here. If you're interested in OpenACC, there are a lot of opportunities for training and for helping you port your code. One of them are these boot camps. These are being organized. There are literally dozens of these being organized over the course of a year. It's a 1 or 2 day event. You come into the site, or it's on site somewhere near you, and there's training and there's hands-on exercises for getting started with OpenACC. If you already have an application that you think is amenable for GPU acceleration, and GPU acceleration by whatever means, there are, again, over a dozen of these a year, these hackathons. These are 5-day events that you come with your team, more than one person, 2 or 3 or 5 people, and your application. You're bringing your code, and you'll be assigned 1 or 2 mentors. You spend a week on site with access to a GPU accelerated system. You can choose if you want to use CUDA, that's great. You want to use OpenACC, that's great. You want to use Python, that's fine. If there's some other method, you can use whatever you want. You'll get help. There'll be other teams there with you, so you get other advice from you see what they're doing. You can learn things from other people. We've had lots of examples. So the number of participants, we had more than, well, these are boot camps, 40 planned here. There's more than 20 hackathons being planned for the upcoming year as well. So, and they're worldwide. There was one in Australia, there's one in India, there were several in Europe. They're all over the place.
Is it free of charge?
You pay for your travel, and you pay for your hotel room,
Sure.
but there's no attendance cost. It might depend on the host site, but so far there's been no attendance cost, right? And some other, here's some selected highlights. So these are some of the codes that they came, they learned, they conquered. And in many cases, they learned to port a small portion of their code, and they got excited. Now they're ready to start moving the rest of their code. In many cases, they learn a lot of things, but one of the things that many of them learn is they haven't been paying attention to performance. They have a badly organized data structure. Their data access patterns are bad. In at least one case, we saw an application got a factor of 3 speed up on a single CPU core. It wasn't 3, it was factor of 12 speed up on a single CPU by reorganizing their data structure. They didn't need GPUs. They didn't need parallelism. They needed to learn how to program for performance. But you learn that sort of thing here too. And okay, let me talk a little bit about ARM and Rome. So what we have today is you can recompile and run across Intel and IBM Power. We've had this for a couple of years. And what we've also support AMD. What we've also added now and have available now is full support for the latest version of AMD. Those are great CPUs. They are awesome. If Intel's not sweating a little bit, they certainly ought to be. And what's coming up next year is full support for ARM. So support for ARM will have all the features, all the same command line options, except those that happen to be really specific to a processor like AVX. But it'll have all the same command line options that you would have for any other architecture. It'll have OpenACC, CUDA Fortran, it'll have all the C++ language features, it'll all be the same. Now these are some of the platform differences I mentioned. This was the one about signed versus unsigned char. That was a real surprise. Doesn't the language define that? No, the language does not define that. That's an idiotic thing. In Linux for x86, the default memory model is small, which means your program is 4 gigabytes. The medium, and their static data has to fit in 4 gigabytes. The medium memory model, the static data can be larger than 4 gigabytes, but the program is still 4 gigabytes. And they don't have a large memory model on x86, but on Power, they use the large memory model. So the programs can be more than 4 gigabytes. What the heck are you doing with a 4 gigabyte program? Obviously, no inline ASM, no inline SSE intrinsics, that's not going to port. But these are platform differences we found when we were porting from x86 to ARM, to Power into ARM as well. So it's a handful, it's under a dozen. Now this is our vision. I have visions. Where are we going for supercomputing in the future? Programming supercomputers. So I'm doing programming model, I'm doing programming languages. So I don't particularly, okay, what we're missing here is, for programming GPUs, for instance, you could use CUDA, you can use directives. Wouldn't it be great if you didn't have to? So here's a little sidelight. Anytime someone says to you, you just do this, you just add this directive, you just add this keyword, you just do this, what they're really saying is, you must do this. You must add this directive. You must add this keyword. Wouldn't it be great if you didn't have to? Wouldn't it be great if your parallel algorithms in C++ just ran in parallel on a GPU? Wouldn't that be great? That would be kind of the optimal, right? I'm programming in C++. I'm not doing GPU programming, I'm doing parallel programming. Or if you're a Fortran programmer, if you're a true C++ bigot, you're going to say the F word again? No, Fortran is a live language, and it's very important in many applications like VASP, like almost all the weather codes. But Fortran has parallelism as well. And wouldn't it be great if the Fortran do concurrent just ran in parallel on GPU? So this is the direction that PGI is moving into. And you'll see some of this coming in the coming year. If you come to the NVIDIA booth at the developer demos, we have a demonstration of the parallel algorithms for C++ running on a GPU. Now, what this doesn't do is let you control data placement. How does the data get to the GPU? What we're hoping is, in some point in the future, we'll have true unified memory, either physically unified between your CPU and GPU, or logically unified and integrated well enough that you won't notice the data transfer costs. We're not there yet. Until we get there, we might need to augment the language. So these directors they're crutches. They're basically filling gaps in the programming language. And so you might need to, for the time being, add some directives to control data movement and then use your parallel algorithms. And then, as you profile the program, there will still be cases where you want to dive into, there's some algorithm you need to change, you want to change the algorithm to take advantage of some feature on the device you're targeting that's not available from this programming model, like, say, tensor cores on a NVIDIA GPU. You want to use tensor cores, you're going to have to dive into the CUDA level. So all of this has to be interoperable as well. But most of the program should be written in standard parallel C++ or C, and that's the direction we're going in. And you come to the booth and see what we have today, and come back next year, and hopefully by next year you'll be able to actually use it. And there was a nice talk about this in the NVIDIA theater as well. You can go look this up there, and that was it. So thanks. If there are any questions, I'll take any.
All right.
Does it offer any support
Thank you,
for what
Michael.
happens with the dependencies when you have nested algorithms?
When you have what algorithm?
Recursive algorithms?
Okay, so the question was, does it have any support for dependencies when you have like recursive algorithms? So that's an interesting point. So this isn't auto-parallelism. There is auto-parallelization in the compiler. And if it finds a dependence, it will run that sequentially. Okay, sequential, if the whole thing is sequential on a GPU, that's very, very slow. GPUs as sequential engines are really slow, as I guess you know. So, but it will report that to you, and that's one of the minfo message that would come back. Okay, there's no fancy recursive solver except for reductions, like summations and min reductions, right? So, okay.
Hey, Jackie here did find a mistake in your code. We'll talk about it later.